So let's say that I have the real number line here, and let's say this is the point that represents the origin 0. So I have that f of t gives you the position of a moving bug, at time t. Am I making sense? So f of t here represents the position of a moving object at time t. So let's say we have a bug that satisfies the following: that at time, let's say at time a, so a is some time. At time a, the position of the bug is this point. So f of a is that point, the position at time a. And also let's say that the position of the bug at time b is also the same as f of a. So that means I'm saying that the position of the bug at time a and at time b are the same. And let's just assume that a is less than b. Okay, so b is a later time. Okay, so f of a, the position of the bug at time a and time b, they are the same. And what I want to, so the problem is then this is the problem, that prove that when you know what, before I even, let's say prove that the velocity of the bug must be zero at some moment c between a and b. So we are concentrating on the motion of the bug over the time interval from a to b, and we are assuming that the position of the bug at time a and time b are the same. And what we are saying is that show that the velocity of the bug must be zero at some moment in that time interval. Intuitively, it should be clear to you why that's the case. I mean, let's say there might be more than one moments where the velocity is zero, but I'm saying there is at least one. And it should be intuitively clear why that's the case, because let's say, well, at time a the position of the bug is right here, right? It's on the line. Let's say this is a one-dimensional world. Okay, so there are no two dimensions here, and the bug can only go back and forth on this line. So it could go like this, right? It could start going to the right or left. Let's say it goes to the right, but then at time b it's got to come back to b, right? So it's got to come back to the same point. So maybe it goes like this, and it can backtrack, right? Or I mean, it could also backtrack again. I don't know how many times, but eventually it's got to come back to the same point, right? Because we are assuming f of a and f of b are the same. Is everybody clear? And there are two more assumptions here that we have to make. So assumptions. One assumption is that the motion is continuous. The bug's motion is continuous. So what do I mean when I say that the bug's motion is continuous? It means that it moves in a continuous way That is, suppose that at some point the bug comes right here, and right after that moment it cannot jump to another point. Am I making sense? So, the bug is a very boring bug. It doesn't know any black magic, okay? So it cannot be the case that, so what I'm saying in terms of, at some time, let's say at time 1, the bug is at a position, right after that it couldn't be at another point which has to be a jump from that point. Am I making sense? So it's a continuous motion, and 2, the velocity is defined everywhere in that interval. So the velocity is defined for all t in that interval. So what do I mean by that? I mean that the velocity exists at any given point. You might say how it may not exist. Well, it may not exist if something like this happens, that the bug is moving and then someone slaps on it, and then let's say at the moment when you're slapping it, the velocity is 2. But at the moment you slap it, all of a sudden its velocity becomes, let's say, -3. Am I making sense? So right at the moment of hitting it, the velocity wouldn't exist. Does that make sense? So nothing bad happens. So basically, number 2 means that nothing bad happens to the bug. Okay. Okay. So these are the 2 assumptions, and then we are trying to prove that the velocity must have been 0 somewhere. So notice that what does that mean? It means that which should be intuitively clear, right? Because you're moving, the bug is moving maybe to the right, but it has to come back to the same point, right? So as it moves, at some moment it has to go back, right? So right at that moment the velocity should be what? The velocity should be 0 at the moment where it starts to go back. Am I making sense? Which is intuitively clear, and if you ask a physicist or a long time ago, they would try to prove it by doing some sort of experiments in the lab, right? They will make an experiment and they will say that yes, that's true from their experiments. But so but in a math we don't work with tools or labs or something. So how do we do it? Well, we just do reasoning. We do deductive logic to show that that's indeed the case. So how do I show that the bug's velocity should be 0? Okay. Well, so let's prove now that the bug's velocity should be 0. To prove that the bug's velocity should be 0 somewhere, there are a couple of cases. We have to do it case by case. Okay. So case number 1. Case number 1 is basically that it's a really hot day outside, okay, and it's like noontime or 2 p.m. when it's really, really hot, and the bug is being lazy. If you go to the zoos, right? If you go to a zoo at 1 p.m. or 2 p.m., you'll see that nothing exciting is happening because all these animals are just being lazy. Okay, so let's say that's the case with our bug. The case number 1 is that the bug is lazy, okay, because it's tired, and which means that it doesn't move, right? It doesn't move means that at time A, it is at f of A, and it never moves. So its position over the time interval from A to B is always f of A. Am I making sense? Which means that the position function is constant. So if I say the position function is constant, it means that the bug never moves, right? Is that making sense? So the case 1 is that the position function f of t is a constant function. So where c is a constant. Well, in this case, obviously velocity is 0, right? So in this case, for sure the velocity is 0. So in this case, we know then the velocity, let's say, denoted by v, and the velocity of the function, velocity is given by the rate of change of the position, and the rate of change of the position is the derivative of the position function, and the derivative of the position function in this case would be 0, not just at one moment, at any moment in that interval. So for any t in that time interval, the velocity would be 0 in this case. So I have really nothing to prove. It's obvious that the velocity should be 0 at any moment, not just at one moment. So that's case 1. That's the trivial case. That's easy to understand why the velocity should be 0 at some moment. Okay, case number 2. Case number 2 is a little bit more difficult, which is, so the case number 2 is that the position, so the bug is not being lazy. Maybe now it's the evening time and the temperature has dropped. Now he feels more energized to move. Okay, and so the bug maybe because the bug moves wherever the temperature is less. So it's going to move to a place which has less temperature, let's say. So the case number 2 is the bug moves to the right, which means the bug is moving away from the origin. Am I making sense? Initially, the position is at f of a, right? So from f of a, let's say it moves to the right. It means that the position is what? Increasing, right? Am I making sense? So in this case, we say that this is the case where the position at certain time. So let's say, so you have the position at time a, and let's say there is a time t0 where the position is bigger than the position at time a. In other words, the bug must be moving to the right from f of a. So t0 inside of that time interval. So what I'm assuming here is that the bug moves to the right, let's say. The bug moves to the right from f of a at some time. So maybe initially it might be the case that, let's go back to the picture. Initially from f of a, the bug may go to the left, but it comes to the right again and goes beyond f of a. Okay? So if that's the case, the bug moves to the right of f of a. Remember, we are assuming that the motion is continuous, right? So the position function must attain a maximum value. That is, think about the rightmost point that where the bug goes during this interval, right? So as the bug moves, because it's not a constant, it's not being lazy, it moves, right? So think about the largest point it reaches during that time interval. The largest position it reaches. Am I making sense? So in this case, f, the position function attains absolute maximum at some time c in that interval. So this is so at time c, the bug reaches the rightmost point on the line. Okay, the largest position it achieves is at time c. That's what I'm saying. Am I making sense? So if it moves to the right, there is a largest position that it achieves during that time interval, and that's the absolute maximum value of the position function. Well, what do we know about absolute maximum value of a function? If it occurs inside of this interval, it's also a local maximum value, right? So then we know that f of c is a local maximum value as well, right? Am I making sense? And if it is a local maximum value, what do we know? We know that the derivative of the function at c should be what? Remember, if I have a local maximum value at c, right, and the derivative exists at c, then I know that c has to be a critical point where the derivative is 0, right? Am I making sense? If you have a local maximum value at c, right? Remember Fermat's theorem that I gave you. If you have a local maximum value at c, the derivative must be 0. Okay. So we know that the derivative is 0, which means that the velocity at time c is 0. Am I making sense? So that shows that there is a time c where the velocity must be 0. What is case number 3? The case number 3 maybe from f of a, the bug starts to move to the left. Am I making sense? So the case number 3 is the bug moves to the left from f of a. In that case, you know that there is the bug will achieve a smallest position, right? The least position of the bug as it moves to the left from f of a. You can think of that there is a least position of the bug, right? It achieves the least position before it comes back to f of a, right? Remember, it has to come back to f of a at time b. So if it starts to move to the left, it has to come back to the same position. So it achieves a smallest position. And the proof goes to the same way. At the smallest position, that's the smallest value of the position function, which means that's the minimum value. And that's the local minimum value. And at the local minimum value, again, you have a critical point. And the derivative must be 0 there. Is that making sense? So the proof is similar to case 2, except that instead of maximum value, you're talking about minimum value, similar to case 2. Okay, so I won't go through the details, but let me show you a graph, a possible graph of the bug. So let's have x-axis and the y-axis, and let's say at time a the position is right here, at time b the position is right here. So this is the position of the bug at time a. So this is the t-axis, this is the y-axis is the position of the bug at time t. So I'm drawing the graph of the position function. So at time b it is right here. Remember, at time a and time b, the position are the same, right? The position at time b is the same as the position at time a. These two positions are the same. So what is a possible graph of this function? Well, this is the line segment joining the two. So case number 1 was that the graph of the position function is this. Case number 1, that the position, the bug is lazy, it stays at f of a all the time, so it's a constant function. in that case, the velocity is 0 everywhere. The derivative is 0 everywhere. Now, if the position function is not constant, maybe from the time f of a, from time a, let's say the bug moves to the right, which means at f of a, this is the position. Then, if it goes to the right, the position is increasing. So, the graph will look like the following. The position increases, and then it cannot go to the right forever because it's got to come back to the same point f of a, because our assumption is that at time b it comes back to the same point. So it cannot go to the right forever, it's got to come back. So maybe it's going to go beyond f of a again, but at some point it's got to come back, right, to f of b. So my point is, it's going to achieve a maximum value somewhere. So at that moment where it achieves the maximum value, at that moment the derivative must be 0, which means the velocity must be 0. Another possible graph would be similar, except the case 3 means from f of a, instead of going to the right, the bug may go to the left. If the bug goes to the left, it means that the position is decreasing, right? So instead of from f of a, the position decreases like this, and maybe it goes like this, okay? I'm just saying these are possibilities. In any case, when it goes to the left, there is a point where the position function would be the least, okay? The position would be the least, and at that point again, the tangent line would be horizontal, or the velocity must be 0. Am I making sense? Is everybody okay with that? What we actually have proved here, okay, what I have actually proved here is the Roulet's theorem. Except that in Roulet's theorem, I took the function to be the position function of the bug, because I thought it might make the proof more intuitive for you. So here is again, let me state the Roulet's theorem again for you. So Roulet's theorem says the following. So Roulet's theorem says that the following. Let's let f be a continuous function on an interval from a to b. This is a closed bounded interval. And assume f prime of x exists for all x in this interval. Also, another assumption is that the value of the function at a and the value of the function at b are the same. Okay? So f is any function which is continuous and it is differentiable over the interval, and the value of the function at a and b are the same. Then we know that the derivative must be 0 somewhere. Then the derivative of the function at c would be 0 for some c between a and b. So for some c between a and b. So for some c between a and b, the derivative must be 0. So in the case of the bug, the function is the position function. And if you think about the conditions here, is that number one condition is that the function is continuous. Our assumption there was that the motion was continuous. Here we are saying that the derivative must exist at any point. There, the same thing means that the velocity is defined everywhere. Okay? Nothing bad happens to the bug. Okay? No one is slapping the bug or anything. So the derivative exists everywhere. Okay, so that's Rolle's theorem.